Okay, anyways, so we did this yesterday. So let me just recall the important definition. So we have a proof system. That means we have alphabet, language, so strings we want to write down, axioms, and the derivation rules, so the proof rules we call them. And then we know that the definition of soundness, or the same as correctness. We say a proof system is sound or correct if everything you prove in your proof system is true. So every proof you make, you start from axioms and you build your proof. Whatever you prove is true once you consider a model, right? Now, consistency was something that you do not prove contradictions, basically. So this means that for no predicate W, you prove W and you disprove not W. So if this does not happen, then you're consistent, right? And complete means that for any predicate now, for any W, you either prove W or you prove the opposite of W. And then we saw that if your language is complete, then everything you can prove is decidable, meaning that if I give you a string, you can tell me whether you can prove it or not. How? You just enumerate all possible proofs, and if your proof system is complete, you either find W or you find not W. So you find one of them, and so you give the answer accordingly, right? So if you find not W, then you say no, 0, and if you find W, you put out if you find the proof, you put out the last thing that your proof produced, whatever. Yeah, here it is. If W appears, accept. If not W appears, you reject. So, and then very importantly, we said that now if you have your proof system is correct and complete, then all the predicates which are true are decidable. So how do you do this? Again, you enumerate everything, and since the things that can be proven is decidable, the correctness here means that if you can prove it, it's true. So you either prove W or you prove not W. If you prove not W, it's false. If you prove W, it's true. So basically you can do this as well. So this is a important observation, that the truth, so if your proof system is correct and complete, meaning everything that it proves is true, and in addition it either proves W or not W, then you can algorithmically decide which statements are true or not. Okay, because you can decide which ones can be proven, and if it's proven, it's true. So either it is proven or not W is proven, then it's false. So you can do this. And now last time we mentioned the incompleteness theorem, which is now if you have any proof system that is as expressive as elementary number theory, that means that it extends elementary number theory. So it has more axioms, maybe it can express everything you want to write down in natural numbers. It can also write down, but maybe more. So it has maybe a bigger alphabet, bigger language, more axioms, and more derivation rules. But if such a proof system is sound, again, sound was same as correct, so everything it proves is true, then it is incomplete. Meaning there will always be a statement or predicate such that you can neither prove it, and you can also not prove its opposite. So you can neither prove it nor disprove it, basically. And let's see how are we going to prove it. We're going to use the halting problem, right? So what we are going to do, we're going to reduce halting problem H to T. T here is just true statements. And let's assume, let me explain lemma 5, and then I'm going to show you how it proves the incompleteness theorem, and then we're going to proceed to prove lemma 5. So here is lemma 5. There is a total computable function. So total here means it's defined everywhere, and computable means computable in our sense, right? It can be computed by a Turing machine. So there is a total computable function, H, such that, oh, there's supposed to be a star here. So there's supposed to be a star like this. So maybe it's better to write this in a different way, because but basically what it does, it maps string hashtag string. So maybe it's better to write h like this way. You take b star, cross it with hashtag, and then again you take b star. So it's a map from something like this. Maybe it is better to write it this way instead of writing this. So it basically, the inputs that h takes is something like this. So you have a string, then you have a hashtag, and then you have a string again. So it takes inputs of this sort. Any string, hashtag, and any string. So h is such function. It takes the input and it outputs a statement about natural numbers. So it maps this thing to L, so some statement. So maybe any x, there exists y, that x plus y is 0. I'm just giving you a crazy example, but this is... So it inputs, as an input, it takes in binary string, hashtag binary string, like this, and it outputs some statement in natural numbers. In LE, we constructed LE. LE contains statements. These are strings, but they are just statements about natural numbers. We think of them as statements about natural numbers. Okay, so what? So h is such function. So the lemma says that there exists such a function so that HUW is true if and only if Turing machine U started with V holds. So this might seem weird on the first glance. So this says that, okay, you have now U, some binary string, and V, right? Right, so you have binary string, hashtag V. Now you apply H to this. This is a statement about natural numbers, right? Some statement, I don't know. For example, this one. For any x there exists y, that x plus y is 0. This is false in natural numbers. However, our lemma says that you can construct a sentence in natural number which is true if and only if Turing machine U started on input V holds. Okay, let's see. What would this entail, basically? So I have to tell you some statement in natural numbers which is equivalent of me saying that U started on V holds. So I want to say this sentence that Turing machine U on input V holds, but I want to say it in the language of natural numbers. In the sense that this statement that I will say in natural numbers will be true if and only if U on V holds. So I want to say U holds on V in the natural numbers, basically. And let's say I can do this. Let's say I can do this. Now, why does this prove the Gödel's incompleteness theorem? So let's say I can do this. Now, ZE, which is S in question here, or let's say proof system of natural numbers. Let's assume it is complete and it is sound. It means that ZE is complete and sound, means that when I talk about natural numbers, I can prove everything or disprove. So complete means I can prove it or disprove it. And sound means that everything I can prove is true. Let's assume both of them happen. Complete and sound. Then I just proved that if something is complete and sound, the true statements is decidable. That means the true statements in natural numbers would be decidable. That means the algorithm, if it's complete and sound, I can just enumerate all proofs, see which ones can be proven, which statements are proven, and then everything can be proven or disproven, so I know the true statements. That means T would be decidable. T is decidable if I have such H, means I can always say whether MU on V holds, because H of UV is in LE, and this is a statement about natural numbers, so I translated my Turing machine to natural numbers, so now I can say if this statement is true or not, if true statements are decidable. If true statements are decidable, I can algorithmically tell you if HUV is true or not. If I can tell you such that HU is true or not, then by this lemma, I can tell you whether MU on V holds or not, and I know this is impossible. So, my assumption that ZE is complete and sound is false. So, if I assume ZE is sound, which I have to assume because otherwise, either it's not sound or not complete. So, I kind of assume that it's sound and I say that it's not complete. Okay, let's pause this and say this. So now the whole incompleteness theorem, the first one, hinges on constructing such H, which is better written this way, because this way you also have 0, 0, hashtag 0, 1, hashtag, many hashtags. But if you write it this way, you only have string, hashtag, and string. All right? So now the whole point is to construct the H, and there's a comment that in MIT textbook this is skipped, but at KIU we do this anyway. Okay, so this is what we want to prove, that there is a total computable function that blah blah blah. So we only work with one tape Turing machines, so our MU, this U Turing machine, is one tape, and V Turing machine, V input is just on one tape, because we know it suffices. So what I want to do is now to say the sentence MU started with V holds, to say this in the language of natural numbers. In order to do this, first I want to decipher what it means. What does it mean that MU on V holds? MU, which is a Turing machine with states, alphabet, transition function, start state, and end state, this is MU, holds on V means the following. There exists W, a string, which is K0, K1, K2, KT. These are configurations. The start configuration, the next configuration, the next configuration. So there's a list of configurations separated by, let's say, a $sign, such that my W is a string that consists of letters, states, and, well, I use dollars here. So it's a string in letters, states, and dollars. So I have the string such that K0, the first configuration, is the start configuration. So it has bunch of blanks, however many I will need. Then it has a start state, and V is written out. The V string is written out. Let me enlarge this. So MU on V halt means that you have the list of configurations. K0 is this. Every next configuration, so KI, the KI plus 1 is the next configuration of KI. So K1 is the next of K0, K2 is the next of K1. And next here means that there's a transition function that goes from KI to KI plus 1. I will also, in addition, assume that all configurations are of the same size. I can do this because, look, so let's say initially if I put 3 B's here, I don't know, 0, 0, 1. If I put enough B's here, that's what I mean. I will never go beyond B's. So the next configuration is maybe again B, 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 and maybe 0, Z, 1, 0, 1, I don't know, B, 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 B. So this means that the transition function here was that on Z0 and 0, it went right and overwrote it with 0 again or whatever, right? So, but if I write enough B's, all of these configurations will be of the same size. If your state never goes over the B, if you write enough B's, they will all be of the same size. So I can assume this. I can assume that each configuration here has the same size. Then, number 4, in no configuration is the state first or last element. This is exactly the assumption that Z never goes to here or here. I have enough p's written. And the final one is that the final configuration kt is an end configuration. The state is an accepting state. So if these 5 things happen, even though 3 and 4 are redundant, if these 5 things happen, then I'm guaranteed that mu started on v holds. Also for the recording. So now I wrote these 5 steps. So the question is, why would I want to do this? So I will translate step 1 into natural numbers. So I will construct a sentence about natural numbers which is true if and only if number 1 is true. Then I will do it for number 2, 3, 4, and 5. And so let's say I constructed sentence, again I can't do this, sorry. So let's say this is sentence A1, sentence A2, A3, or statement, for that matter, A5. So I have 5 statements in natural numbers which are equivalent that, let's say statement 5 is that the last configuration here is an end configuration. So this is a statement 5. And then what I will write is A1 and A2 and A3 and A4, this is and A4 and A5. So this sentence now, sentence A, which is this and this and this and this, which I can write in natural numbers. I was allowed to use and. This statement will be true if and only if all 5 of them are true, which is true if and only if mu on v holds. If I construct A1, A2, A3, A4, and A5. Now the whole point is to translate the states and everything into natural numbers and these things into statements about natural numbers. And I do it as we did this before. This is trick by Goedel, by the way. So what I'm doing now is I'm translating Turing machine into numbers now. How do I do this? I take how many alphabet symbols I have. I also take number of states. So my Turing machine has number of alphabets. This is finite. And the number of states, which is also finite, and plus 2. So if my Turing machine has 5 states and 17 alphabet symbols, 5 plus 17, this is 22, plus 2 is 24. So I'll take the prime number that's bigger than 24, which is, let's say, 27, is that prime? 27. So I take a prime number which is bigger than this plus 2. So now I have a prime number p, and what I do is I take a function psi so that to every symbol, I did this before, so you're probably aware of this. So for every alphabet symbol and every state and every dollar, I assign a natural number from 1 to p minus 1. So for example, so if my states are Z0, Z1, Z2, and my alphabet symbols are 0 and 1 only, then so I have 3 states, I have 2 alphabet symbols, and then I plus 2, I take plus 2, and so this is 7, and I want a prime number which is bigger than 7, and next prime number to 7 is 11. So I take p equals 11, right? And I just do this assumption. Psi of Z0 is, I don't know what, 1. Psi of Z2 is 2. Psi of Z3 is 3. Or Z3 is no longer, so it's Z1 here and Z2 here, like this. Psi of 0 is, let's say, 4, and psi of 1 is 5. Okay, no problem. And I will also set the psi of epsilon, so the empty string is 0. So for every state and for every alphabet symbol, now I have a natural number. Right? So for every state and every alphabet symbol, I have a natural number. And for empty string, I take 0. Right? And what I do is now I extend it to strings as I did before. So now if I have a string in natural, so in string that represents a configuration, so let's say I have a configuration like this, By the way, there's also a blank symbol, I forgot. There's probably a blank symbol here also. So maybe psi of blank is also something. 1, 2, 3, 4, 5. Maybe let's say 6. It still works. So blank symbol is also in my alphabet, which I forgot. So now if I have a configuration like this, I can translate it into natural numbers. How? Because z0 goes to 1, z0 goes to 1, 0 goes to 4, 1 goes to 5. So I just translated it like this. But I translate as if these are, so if I have a string here, I translated it into base with power p. So we did this trick, it's the same trick again. So if I have a natural number like this, 1, 2, 3, 4, 5, not a great natural number. So 3, 2, 1, 4 in our case. This actually, how I interpret this is that it's 3 to the p to the power 3, right? Plus 2p to the power 2 plus 1p plus 4p to the power 0. Okay? So I did this before, right? So each number is now comes from, so this thing will again be translated into power, so into, let's say, even the easiest thing to think about is the one we used to, if p is decimals. However, I do not allow this. I want my p to be a prime number, but let's just ban it for a moment and think of p as decimal numbers, and then we do this translation as we did before. By the way, I'm kind of skimming over these things because we did this before, but let me pause this and ask you. Yeah, the artifact of this is, if p is, let's say, I don't know, a big number, let's say 31, that means that there might be one symbol, let's say blank symbol or something else. So maybe I have some weird symbol in my alphabet, let's say question mark, and this will go to maybe 27. So two symbols on the natural number side can represent one symbol here. Then this guy, for example, this blank, will be represented by 27, I don't know what blank was, maybe 5 or something. However, 275, this natural number, represents just two symbols, question mark and blank. This can happen. It's actually good that you guys are saying this kind of thing, because so you remember, that's why I do not dive into details. It's the same exact thing as we did before in case of 16, but here the only difference now is that I require my p to be a prime number. But I can always do this. It will be apparent why I want this to be a prime number, but this is the only difference. Before we took hashtag A, hashtag Z, and then I took just the first number, which was bigger or something. But now I require first prime number, which is bigger, and I write it in base p. Right? So strictly speaking, if you have a string W, you have W as 1. So the string like this that I wrote here, the concatenation, but each one basically represents the power of a prime. And for a shorthand, right, what would be a hat? So now, by a hat, why doesn't it write? Yeah, by a hat, I mean psi of a bar. Recall what this is. Psi of a is a natural number, right? Let's say it's 3. Just for example, let's say it's, I don't know, 17. Psi of a is 17. The a is a signed number 17. And now, what is bar? Remember, this is just sum of ones 17 times with appropriate parentheses like this. But now this, as a bar, is viewed just as a string in the language of natural numbers. This is just a string. It's a formal string. So a hat just represents a formal string in the language of natural numbers that corresponds to symbol A. So in reality, yeah, this is again, in this case, 17, but think of it as a string 17. Okay, we do this. And now comes our first concatenation lemma. So what does this lemma say? Is that there exists an arithmetic predicate, so a string in LE, particularly a predicate that has a true or false value, which is denoted by square brackets, v equals xy, such that for all strings v, x, and y, if v, so let's try to understand this, because this is basic. So now I have string v, string x, and string y. These are all strings. They're supposed to represent some configurations or something. So v is a concatenation of string x and y if and only if, now v can be translated to a natural number, right? X can be translated to a natural number in base power p. Y can be translated into natural number. So there exists a statement, which I denote by the square bracket, that this statement is true if and only if v is a concatenation of x and y. Let me pause this again. Okay, let's look at base 10, for example. Let's say I have a string 0, no, let's not do 0, 1, let's do $1B. And let's say this is 10, this by psi, this goes to some decimal number. Let's think of decimals for 874. Because 1 goes to 8, B goes to 7, dollar goes to 4. And let's say now I have another string, B, let's say 0, and this goes to 7, 1. Right? So let's say I have this. This goes to this. And now I'm saying, where does this guy go to? Yeah, it's going to be something like this. Exactly this is what I'm saying now. What I'm trying to prove is that $1B B0 is now a concatenation of $1B concatenated with B0 if and only if I have to say that even 87471 is equal to what? خب اگه გოთკუთხედი რა უნდა იყოს? Exactly. This is what it is. This square brackets should be this statement here. This statement is true if and only if this statement happens. So the square brackets just denote this statement. But now this statement, think of it as just a string in the language of natural numbers. So exactly, so what you guessed, here comes the punchline here. Where is my enlargement? So v equals xy, the square bracket, is by definition what? Look. Now let's look at the first line, what it says. Either y is 0 or v is x. Can you tell me why did I wrote this? What you told me is this here. You told me that v is a concatenation of x and y if v equals y plus u times x, and u is the power of p. This is what you told me. P in our case was 10, length of, so this here. Why did we, so yeah, let me ask you a question here. Why did we put, where did this 2 come from? How did you know that it was supposed to be 2? So it was, so in our case, this is y, this is x, and this is v. So this is the length of y. This is p, so it's p to the power length of y. Okay? this is exactly what this thing says. So if v is equal to y plus u times x, and u is a power of p in the power of length of y. So this is exactly what you said. But what about this one? What does this mean? Exactly. If the second guy does not exist, what is the psi of... So second guy does not exist means that y is epsilon, right? Remember I said that psi of epsilon is 0. So this is a number that corresponds to epsilon, right? As we did here. If I would have had epsilon here, this goes to 0. I know this by psi. So this is exactly what this guy says, that y is 0. That means y, whatever y was reflecting as a natural number was empty set. So y is 0 and v is x. This is possible. Or y is not 0 and there exists u such that v is u, y plus u times x, and u is the power of y. This is all there is. What's the problem? Why is it not finished? This is a string. So what I'm claiming is that this is a string in the language of natural numbers, which is true if and only if v is a concatenation of x and y. But what the problem is that not everything that I wrote down here is allowed in the language of natural numbers. What is not allowed, for example? Something like this. Yeah, this we never allowed. We never allowed writing a power of something, and we never allowed writing p, what is p, and stuff like this. So now I have to clarify that I can still write these things. This is the tediousness here. So how do I write in my language u is a power of y? So what I'm claiming, and I have an example here as well, maybe you get it without an example. U is a power of y is equivalently said is, so yeah, u is not just some power of y, it's a power of in the length of y. So u is p to the power length of y, if and only if u is a power of p, and u sits between u is bigger than y and u is less than p times y. Can you guess why this is true? Let me pause this and record. What does this thing basically say? Think about it. It says, I cannot write. So this thing says that u sits between y and p times y. It's like this. This is what I said. And let's say u is a power of, and I'm claiming this is, if u is a power of p times y, let's say, then this says that y, you have here p times y. Is this true? If you take just a log of everything with base p, what will happen? Ayak ra ikneba. აქ შუაში ვინ იქნება? სიგრძე. Here plus 1 basically, right? Log pp. What is this? ეგ y-ის სიგრძე არ არის? ქვემოთ. ეს ფუძეში ჩაწერილი y-ის სიგრძეა რა. და ეს სიგრძეს პლუს 1. So this is basically length of y. If y is written in base p, this is length. If you write y in base p, this is the length of y in base p. This is just length of y. This is length of y plus 1. So this just says that length of y sits between length of y and length of y plus 1. And this is reversible. Let me give you another example. So for example, again, let's take p equals 10. Yeah, let's look at the example. Maybe this is better. So I want to say that u is 10 to the power x, right? And I want to guess that the x is 3. So, for example, in my case, here it's u is 10. Well, u is 10 to the power x. And it's between 456 and 10 times 456, right? For p equals 10. This is an example for p equals 10. Y, in my case, is 456. Length of y is 3. P is 10. It's not a prime, but it's not relevant here. Then u is 10 to the power x. 456 is less than 10 to the power x. This is what this guy says. 10 to the power x is less than 10 times 456. And 10 to the power x sits between 456 and 10 times 4. And if you solve this for x, you will get that x is 3. Here as well, like if y is less than u and u is less than p times y, if you solve this, you will get that if u is equal to p to the power y, then p to the power x, that x has to be the length of y. Let me repeat this. All right, we lost the recording of the second hour, so in-class recording. So what I'm going to do, I'm going to do a very quick rundown so you at least have a chance to look at slides and just do really quick comments of what we covered. So this happened before, but once again, unfortunately. So okay, I think we stopped here, the recording stops here. So we kind of try to convince ourselves that u is equal to p to the power of the length of y is equivalent to u is the power of p, and these two things, right? And now as we defined L of E, the language of statements of elementary number theory, these two things are not allowed. Y is less than u and u is less than p times y. So how do we write them? Very easy. You can see that u is less or equal to y is equivalent of saying that there exists some r such that u is equal to y plus r. In the same way, u is less than y is equivalent to u is less or equal to y, and u is not equal to y. Okay, and so that means that these two things that written here can also be said in the language of LE. These are just predicates in LE with all the allowed things. The only thing left here is u is the power of p. We also have to say it in the language of LE. And how do we say that? U is the power of p. You say that for any r and any s, if rs is u, that means u has divisor r or s divides u, then r is equal to y, and p divides r. So r is basically a power of p. Okay, and so you do not have to say the same thing for s because this is symmetric. And p divides r, so there's one component here that p divides r is equivalent of saying that there is s, that r is p times s, p being with a bar, meaning it's the p many additions of 1, so the string of p many additions of 1s. So now we have said everything. So this here, this bracket is now defined, v equals xy. So everything here, we're just defining this part. So everything is defined, and then we have defined this predicate that satisfies this lemma here. And of course, you can do it for 2, 3, and many more components, meaning that you can concatenate 3 things and 4 things and so on. How do you, for example, concatenate 3 things, x, y, b? Then that means that there exists w, that w is a concatenation of x and y, and u is concatenation of u and v. So you concatenate the concatenation once again. All right, so now we go on to, now since we have a concatenation in our hands, now we actually begin to prove our lemma. And the idea is to, as you recall, the idea is to actually say what it means that the Turing machine halts in the language of elementary number theory. So I want to translate the sentence that Turing machine halts on input v in LE, and then translate, meaning that the sentence, the string that I will translate to will be true if and only if the machine halts. So first, for that I actually decipher what it means for a machine to halt. So I have the machine m of u like this, and I have a word. So mu halts on v means there's a sequence of configurations, and I use $ here as an outside symbol, so to as a delimiter between different configurations, K0, KT now, and then these 5 things have to be satisfied. First of all, K0 has to be a start configuration, so I have state Z0 and input V and as many blanks as I need. So if my machine holds, it makes finite amount of steps, so I will just need finite amount of B's on both sides, so I write that amount of B's. So K0 will be that, and then each Ki plus 1 configuration is the successor of Ki according to the successor definition for Turing machines. And then I make an additional assumption that if I write enough B's here, all of the configuration strings like this will be of the same length, of course, because this Z moves around here, but it never crosses the border. And also the fact that it never crosses the border means that in none of the configurations Ki, the state is first or last element. So this is number 4. This 3 and 4, I can make these assumptions. They're not necessary, but I can. And the fact that it holds is that KT is an end configuration, meaning the state is the final state. So what I have to really say here is that I have to write each of these sentences in the language LE, say A1, A2, A3, A4, and A5. These 5 requirements, if I write them in the language of LE, of language of elementary number theory, then I will say, let's say this is A1 and A2 and A3 and A4 and A5, and this sentence of putting ends in between these 5 sentences will constitute a sentence which is true if and only if all 5 of them are true, which is happening if and only if mu on V holds. So I have to write each one of these sentences. That's basically my job. And so I concentrate on the first one first. So I have to write that K0 equals to this in the language of LE. How do I do it? I use the concatenation that I just described. So what does it mean that K0 is equal to BBB? So first of all, I have to say that W is equal to K0 up to KT like this, and K0 is like this, exactly as written in number 1. So this means, basically I write, there exists KMABC such that W, this string here, is equal to, so we continue, so again, so we have to say, so W is equal to the concatenation of the thing whose code is dollar, so this is what it means, then something, K, so K is supposed to encode this whole thing. Then again a dollar, meaning a something, some number whose code is a dollar. Basically, that's what this means, right? It's a number, but it's basically a string. So this represents this dollar, and then there's something M concatenation that represents the rest of this thing. So W is dollar, something, dollar, and the rest. This is what ends with, such that, and this K, this something, this K is supposed to be K0. K is itself ABC, concatenation of 3 things, such that A is the code of bunch of B's, C is also a code of bunch of B's, and B, the something in the middle, is just the code of Z0 and the input. Right? Makes total sense. If this sentence is true, that means that W is something like this, and we're talking about K0. So number 1 will be satisfied. We will do this for 2, 3, 4, 5. But this is the case. But of course, now we have to say these things in the language of natural numbers. So how do we do this? For this, we use this nice little trick that there is a predicate sigma dA, which is true if and only if D codes a single symbol in A. Meaning so D is a number, A is a number, so strings as numbers again. D is a number, A is a number. A is a longer number which codes some string from string coming from here, from the configuration basically. So A codes some configuration, and D is just a number inside A, and I want to kind of identify when does D code one symbol. So in psi minus A, which is just a string, when does the D code just a single symbol? And this only happens if you think about it. So this only happens whenever d is less than p. So let's say if p is 17, we're discussing this example here. Let's say p is 17, right? Then, and let's say I have this psi that codes every symbol here, every string from 1 to 16, right? So some of the symbols here will get 2 digits. That's the idea. And I want to be able to say in LE when they are 2 digits. So, by the way, I mean, there was a discussion about this during the class, and let me just quickly emphasize what is happening here. Even though you have somehow, let me get my pen here. So let's say you might have something like this, 1717, right? Oh, let's make it 6. So you get 1616. So if you write it this way, you're not able to say whether it's 16 and 16, meaning is it 16 times p to the power 1 plus 16 times p to the 0, or maybe it's, I don't know, 16 times p to the 0 and then 6 times p to the 1 plus 1 times p squared. These are two different numbers. But somehow when you write them, we mean that they are represented in base p, so we know, so ambiguity is gone. This thing is not happening in decimals because we know that every symbol has just represents, so every digit somehow represents 1 power. You know what I mean? So if you write, there's no, in decimals, there is nothing that is, there is no power that is represented with 2 digits, but this can happen in if you do in base which has 2 numbers. So if you think about it, if you use base 16, you do not write 11, you use letters. You go up to 9 and then you go A, B, C like this, because you want only one symbol to represent the position of the, so you want to be able to get rid of this ambiguity that I described here. And we also here, we think that this ambiguity is gone. So instead of 16, maybe think of them as written either this way or either this way in the second case. So we kind of know from the get-go what this thing means. However, now let's say it's written in this form, the number, and we want to be able to say that, okay, this 16 represents the single number. Then what it really says that if you have sigma dA, when does d code just a single symbol in psi minus 1a, so in the string, it only happens when there exists E and there exists F such that A is a concatenation of EDF and D is less than P, and D is not 0 because D is 0 if and only if it comes from the empty string. Right? So this is obvious if you think about it. That what I really want to say that there in elementary number theory I can say this sentence that decodes so just one symbol. And here is an example you can stare at. If P is 17, then you have some string. So let's say the string is A1, A14, A3, and A4. This is the string. And then let's say each AI is mapped to I. It doesn't really matter without loss of generality. We can assume that A14 is mapped to 14, meaning to 2 digits. Then let's say A would be 4 times. So if you start from here, this whoever's code I'm looking at, the number I'm looking at will be 4 times 17 to the 0, 3 times 17 to the 1, 14 times 17 squared, and 1 times 17, 3. So basically in my parenthesis notation, this should be something like 4, then 3, and 40. It's like this basically. And now I want to be able to, so I see this, I see that the 14 is like this, 3 is like this, 4 and 1, of course as a human, but I want to be able to say that 14, this D here, is just maps one symbol, and it represents one symbol, and it represents one symbol if it's less than 17. Anything less than 17 will represent one symbol, of course. Because 18 cannot represent anything, because 18 will be 1 and 8 for sure. And this is exactly what it says. D is not 0 and phi minus D is not epsilon, and D is less than P together with this. So you can stare at it and you can see that 14 represents one symbol. So okay, we can do this.
again quickly. And then if you have this is very easy. A equals psi b b b then will be represented in elementary number theory. How? For any d, if d codes one symbol in A, that one symbol is the code of B. So it means it's all B's, right? And the same thing, of course, you can do with C. And for B, this is an exercise I put in. It's very easy to think why. How do I represent the psi z0 of V is, so B is a code of z0v. How? If there exists y0, ys, such that ys is z0, ys minus 1 is you shift the previous, so you shift z0 by 1. It's like multiplying by 10, but I multiply by p. So you add 0 at the end, basically, and then add the code of the previous one. So you're doing basically like this. What is 31 in decimals? It's you shift 3 by multiplying by 10, and then you add 1. So you do the scheme lengths of z0v many times. So for example, then the next step would be, if I want to write 3, 3, 2, 3, this would be 3 shifted twice plus 2 shifted once plus 3. So this is called the Horner scheme, and you just shift, 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 shift until you get the code here. And this is an exercise to convince yourself that this is happening. So this concludes number 1, and then we also talked about number 2 and 3. How do we write these things? That first of all, you have to write that this something is a successor of something. Ki plus 1 is a successor of Ki, and each one of them have the same length. Now we have to code sentence A2, I called it, and 3. How do we code neighboring configuration x and y? This would mean that W starts with something is K0, which will be fixed from sentence 1, because if sentence 1 is true, then R will be fixed as it was in the previous slides. And then we have a dollar sign, something that codes dollar. So we're moving here to K1 now. Then X, dollar, Y, dollar, Z. So I'm here now, such that X codes no dollar. That means X is completely a configuration. Y codes no dollar. That means Y is a configuration. And Y is a successor configuration of X. But now I have to say all this in elementary number theory. How do I do this? X codes no dollar is easy, because for any D, if D codes one symbol in X, that one symbol is not a dollar. So X codes no dollar. Same thing with Y. And this is where we stopped. So I'm going to say this and forget. Well, stop, not forget. Y is a successor configuration of X is very easy. Let me just enlarge this, and then you stare at it and you realize that it's easy. What does this, how do we say this is elementary number theory? Is that there exists V and there exists U, such that this is ORing all possible states and symbols AC. It's ORing them, or this, or this, or this, such that if delta, this is a finite, because this is in Turing machine, this is a finite, it's a finite table of delta. So if delta ZA is equal to Q, it goes from state Z to state Q, overrides A with C and stays neutral. Then what X and Y can be is, if X is U, Z, A, V, well, Z and A are just numbers, basically. You look at the heads, these are codes of Z and V and some string U and V, and Y is again U and V, but however Z is replaced by Q and A is replaced by C. So every time this equals to this, you can get either X is this or Y is this, or X is this and Y is this, or. So all possibilities are possible here. Also in the second line, and also in the third line, where the second line corresponds to moving right, and the third line here corresponds to moving left. And this is just a finite string, because all these things are finite here. This table of deltas is finite. So this is either this, or this, or this, or this, or this, for all possibilities here. And then this sentence on the right is true if and only if the transition happens. All right, then this is where we finished, and I did a quick rundown, and we continue next time.